The year was 2008. The internet was a different place. A sprawling, chaotic library of text and images that was slowly, painfully, trying to transform itself into a television set. Browsers were struggling. They were choking on the ambition of developers who wanted to drag desktop-class applications into the browser tab. The bottleneck was JavaScript. While flexible and ubiquitous, JavaScript was never designed for the heavy lifting of three-dimensional rendering, complex physics simulations, or video encoding. It was an interpreted language, a slow, methodical translator trying to keep up with the frantic poetry of high-performance computing. Google, however, was not interested in slow translation. They were interested in raw speed. They were building an empire on the premise that the web browser would eventually replace the operating system entirely. To achieve this, they needed to break the laws of internet physics. They needed native client. Native client, often abbreviated as NaCl, was a technology designed to run native code, usually C or C++, directly inside the web browser, safely. To understand the gravity of this, one must understand the danger. Native code is the language of the hardware. When a programmer writes in C++, they are speaking directly to the processor, managing memory addresses and instructing the central processing unit to execute operations with zero latency. It is powerful, but it is also lethal. A single error in native code can crash a system. A malicious line of native code can steal passwords, wipe hard drives, or turn a computer into a zombie for a botnet. Allowing this level of access inside a web browser, which visits hundreds of untrusted websites a day, was considered by many security experts to be an act of madness. It was like inviting a tiger into your living room and hoping it would behave like a house cat. Google's engineers, led by figures like Brad Chen, Bennett Yee, and David Sayre, believed they had built a perfect cage for the tiger. This cage was the sandbox. In computer security, a sandbox is an isolated environment where code can run without affecting the host system. But the native client sandbox was different. It utilized a technique called software fault isolation. To use a simple analogy, imagine a high-speed train. Normally, a train the native code needs to run on specific tracks to go fast. If it derails, it destroys the station. The traditional web approach was to force the train to drive on a rubber road at 10 miles an hour to ensure safety. Google's approach with native client was to build a tunnel of reinforced concrete around the tracks. The train could go at maximum speed, but the moment it tried to turn left or right to access memory it should not touch, it would hit the wall and simply stop. The validator was the gatekeeper, a piece of software that scanned the code before it ran, ensuring it contained no instructions that could breach the tunnel walls. The initial impact was electric for those paying attention. Suddenly, the impossible became possible. In 2011, the gaming world saw the release of Bastion on the Chrome Web Store. Bastion was an award-winning action role-playing game with lush, hand-painted graphics and a reactive narrator. It was not a Flash game. It was not a shaky JavaScript experiment. It was a full console-quality title running inside a Google Chrome tab at 60 frames per second. Ubisoft ported From Dust, a complex God game simulation, to the browser. The barrier between the real computer and the internet computer began to dissolve. For a brief moment, it seemed that Google had solved the web's performance problem by bypassing the web's language entirely. However, the silence of the rest of the industry was deafening. This brings us to the controversy, which unfolded like a slow-motion car crash, starting in the legal and standards departments of rival corporations. The first hurdle was the lack of standardization. The World Wide Web Consortium, or W3C, is the body that decides how the web works. They favor open standards that work on any browser: Firefox, Safari, Opera, or Internet Explorer. Native Client was a Google invention, and initially, it only worked on Chrome. Mozilla, the organization behind Firefox and a stalwart defender of the open web, refused to implement it. Their chief technology officer at the time, Brendan Eich, the very creator of JavaScript, viewed Native Client as a black box. He argued that distributing opaque blobs of native code went against the very spirit of the web, which was supposed to be transparent and viewable. This philosophical standoff quickly morphed into a financial burden. Google found itself in the position of having to pay developers to port their applications to Native Client. While the exact figures of these subsidies are buried in non-disclosure agreements, the industry rumor mill suggested that Google invested millions of dollars enticing game studios like Square Enix and Unity Technologies to support the platform. They were trying to buy an ecosystem. But for a developer, the economics were poor. Why build a version of your software that only works on Chrome, which at the time held a smaller market share than it does today, when you could build a native app that worked on Windows or a mobile app for the exploding iOS market? The revenue generated by native client applications on the Chrome Web Store was negligible compared to the billions flowing through Apple's App Store or Valve's Steam. The political implications were even darker. Critics began to compare native client to ActiveX, a Microsoft technology from the 90s that had allowed native code in Internet Explorer. ActiveX had been a security nightmare, a vector for countless viruses and Trojans. While native client was technically far superior and infinitely more secure than ActiveX, the optics were terrible. The web community feared a return to the browser wars, where websites would only work in one specific browser. Google was accused of trying to fracture the web to serve its own operating system, Chrome OS. They were accused of trying to create a walled garden within the open internet, a private fiefdom where Google set the rules of physics. Then came the technical controversy, the specific architectural flaw that threatened to undo the whole project. The original native client was not truly portable. It required the developer to compile their code for the specific processor inside the user's computer. If a user had an Intel chip, they needed an x86 version. If they had an ARM chip, common in phones and tablets, they needed an ARM version. This shattered the write once, run anywhere promise of the web. To fix this, Google introduced Portable Native Client, or PNACL, pronounced Pinnacle. PNACL was a brilliant, sophisticated pivot. Instead of compiling the code all the way down to machine language, the developer would compile it into LLVM bitcode. LLVM, or low-level virtual machine, is a library that is used to build compilers. Think of bitcode as an intermediate language, a universal Esperanto for computers. The developer sends this Esperanto to the browser, and the browser then translates it the rest of the way into the specific dialect of the user's processor. It was a technical marvel. It solved the portability issue. It allowed Google to verify the code was safe before it was translated into the dangerous raw machine instructions, but it was too late. The complexity of the solution had grown too great. While Google was building reinforced concrete tunnels for high-speed trains, Mozilla had been quietly upgrading the rubber road. They introduced asm.js, a subset of JavaScript that was so optimized it ran at nearly half the speed of native code without any plugins, permissions, or security sandboxes. It just worked everywhere. The contrast was stark. On one side, Google's PNACL, a heavy, complex, technically brilliant architecture that required a proprietary plugin and extensive tooling. On the other side, ASM, as a clever use of the existing laws of the web that required nothing new. The suspense of this technological standoff broke not with a bang, but with a handshake. The engineers at Google, realizing that PNACL would never achieve universal adoption without Mozilla and Apple, and the engineers at Mozilla, realizing they needed something even faster than ASM.js, met in the middle. They looked at the PNACL architecture, specifically the use of that intermediate Esperanto code, and they looked at the safety of the web. They decided to kill native client to save its soul. The result was WebAssembly, often called WASM. WebAssembly is the spiritual successor to native client. It takes the core idea running low-level code in the browser and standardizes it. It uses a binary format that is similar in concept to the PNACL bitcode, but it is supported by every major browser vendor, Google, Apple, Microsoft, and Mozilla. When WebAssembly was announced in 2015, it signaled the end of the native client project. Google announced the deprecation of PNACL, and by 2020, the technology was effectively removed from Chrome. The death of native client was a failure of product, but a triumph of influence. While the brand died, the technology reshaped reality. The financial impact of the technology that succeeded it, WebAssembly, is incalculable. It powers the modern web. When you use Figma to design an interface in a browser with the smoothness of a desktop app, you are using the legacy of these ideas. When you run Adobe Photoshop in Chrome, or edit video in a cloud-based editor, or view a complex data visualization, you are relying on the foundational work done to make C++ safe for the web. Companies like Adobe, Autodesk, and Unity have migrated massive, billion-dollar software suites to the web because of the path native client cleared. There is a deeper, almost philosophical impact on humans and the Earth. By allowing heavy computation to move into the browser, we have severed the tether between the user and their local hardware. A student in a developing nation with a cheap, low-power Chromebook can now run enterprise-grade software that previously required a $3,000 workstation because the heavy lifting can be optimized and distributed. It has contributed to the centralization of computing power in the cloud, a shift that has altered the energy consumption patterns of the planet, moving heat generation from millions of offices to massive, cooling-intensive server farms. In the end, Native Client was like a booster rocket. Its purpose was to provide the immense thrust needed to escape the gravity of a slow, text-based web. It burned massive amounts of engineering fuel, generated heat and controversy, and eventually, having done its job, it was jettisoned into the ocean of obsolete code. But because of it, the payload, the idea of a truly powerful, application-grade web reached orbit. It is a reminder that in computer science, being right is not enough. You must also be consensus-driven. But sometimes, being right and alone is the only way to force the consensus to move forward. The code for Native Client no longer runs on our machines, but its ghost haunts every high-performance tab we open, a silent, sandbox phantom, ensuring that the web remains a place where the impossible can execute in milliseconds.